Hello, welcome to another math ramble focusing on the department's May 2023 paper 2 question 10. This is my third attempt at recording this. And it's kind of like a bit of a cardinal sin because the whole idea behind these videos is for me to encounter a question freshly and just talk through how I reason about that question. So really, I try not to do more than one take, right? Because I don't want to take away from the experience of like thinking through different possibilities and hopefully that being a learning moment for all of us. But in this case, what had happened was I started approaching the first part of the question and it all seemed straightforward and intuitive until I realized, oh my goodness, like the result that I'm using to prove a certain thing, is that actually a result that is covered in the syllabus? Is that something that we're taught, or is it something that we have to prove first in order to use it? So the memo went ahead and said, no, baby girl, there's no need to prove the result. It's okay for you to just say that result is what it is without actually showing why it is. So I'm still confused. I've just looked at the Siavula textbook. Siavula, fantastic resource if I haven't mentioned that already. And I don't see that result being proven. So it really is just a big question mark to me at this point. If any teachers are watching these videos, please could you comment to confirm whether this is a result that's covered in the syllabus, or is it just something that appeared miraculously in this particular exam. So I'm gonna start talking through the question and then I'm going to talk about this result that threw me for a proper ringer, and show why that result is actually valid and true, just for fun. And then hopefully I don't need to do any more takes, like, oh my goodness, I can't do another intro for this question. So here we go. Question 10. In the diagram, TR is the diameter of the circle. Okay, so I'm going to begin by highlighting that. So TR is this chord over here, and we are told that is the diameter. TR passes through the center of the circle, in other words. Okay, so cool. Then we're told PRKT is a cyclic quad. So PRKT is a cyclic quad. Okay, then we're told chords TP and KR are produced or extended to intersect at S. So in other words, TPS and KRS are both straight lines. It's not a situation where you go TP and then it bends a bit in a way that you can't see on the paper or something. Okay, so we're being assured that those are straight lines. Okay, and then chord PK is drawn such that PK is equal to TK. So the length of PK is equal to the length of TK. Okay, cool. So first question, prove, giving reasons, that SR is a diameter of a circle passing through points SPR. So I always like to draw the circle, right? So it goes through S, and then P, and then R. So maybe a circle like that. And we're being asked to show that SR is a diameter of this circle. So this is where things got a bit interesting for me, because instinctively I was like, oh, okay, cool. If I can show that this angle is 90 degrees, then surely SR is a diameter of this circle. And I kind of paused to be like, wait a minute, is that actually true? Because the result that we are shown in school is that if you have a circle and it has a certain diameter, that guy, if you subtend an angle at the circumference from that chord, that angle will be a 90 degrees. So to put that more clearly, the condition is that you have a diameter and you subtend an angle at the circumference, and the result is that that angle will be 90 degrees. But what we want to show here is if you have some chord in the circle and that chord happens to subtend a 90 degree at the circumference, then that chord has to be a diameter. There's no other way for that to happen. And I don't know if this converse, because this is what it is, whenever you switch the result and the condition around, that's known as the converse of the theorem. So I'm not sure if I have ever been taught the converse of the angle at center theorem. So I thought that might be a cool thing to look at. Might be completely overkill because, someone might say, yeah, we are in fact taught that in school, so mew mew. But I just thought it would be cool to look at why that converse is true. So just a reminder of what we're setting out to prove. We are setting out to prove that if you have a circle and some chord subtends a 90 degree at the circumference, then this chord must be a diameter, aka it does pass through the center of the circle. So let's see how we could prove that. And I'm not going to go into writing out a proper formal proof, because I saw in the memo that they don't actually even they don't prove that converse. They just allow you to use it as a reason and you move on with your life. So we have our circle, and what we're going to do is do something called proving by contradiction. So we're going to say we have a chord, and this chord does not pass through the center of the circle. Okay. Additionally, this chord does subtend a 90 degree angle at the circumference, right? And we are going to show that nope, it is not possible for this condition to hold. We can't have a chord that isn't going through the center of the circle subtend a 90 degree at the angle. Something is just not going to add up. Or it will only be true under a certain circumstance, and that circumstance turns out to be that the chord does pass through the center of the circle. Okay, so this is what we're starting out with. So since it doesn't go through the center of the circle, that means we do have the center of the circle somewhere here. Another thing, I'm not going to go through different cases or variations of the proof. I'm just going to work with a scenario where the chord is beneath the center of the circle, but maybe as an exercise of your own, you could prove that the same is true if this chord happened to be above the center of the circle or whatever. Anyway, so inspired by the proof that you have to know, proving that the angle at the center of the circle is twice the angle subtended at the circumference, I am going to draw a line that starts at that vertex of the triangle and goes through the center of the circle. Additionally, I'm going to draw these radii. Those radii. So then we know that these are all the same length, and we therefore create a whole bunch of isosceles triangles for us to work with. Okay, so this angle over here, we can say has a value or size of x. So then this angle over here will be 90 degrees minus x, right? In order for them to make up 90 degrees. This angle will also be 90 degrees minus x, because angles in an isosceles triangle, base angles. And likewise, this will also be x, right? Because of this isosceles triangle. Okay, then we also know that this angle over here is an exterior angle, right? Again, if we look at this triangle, right? This is an exterior angle, which is equal to these two added together. Okay, so this will be 2x, right? And then similar reasoning if we look at this triangle instead. Okay, then this angle will be 180 degrees minus 2x, right? 90 plus 90, which is 180, minus x, which is minus 2x. Okay, so we now see that this angle at the center is actually going to be 180 degrees minus 2x plus 2x, which is 180 degrees. So in fact, these arms of the triangle are not arms like that, because 180 means a straight line. So in effect, you can imagine that these arms are actually like this, meaning that this chord is also in line with the diameter, right? So just imagine yourself grabbing these two corners of the triangle and stretching them out until this angle is 180 degrees. In other words, until the triangle is flat or is just one straight line. So that means that the chord that subtended the 90 degrees can only be a 180 degree angle that is going through the center of the circle. So that is, I mean, check me if that is an adequate proof. But what we are showing, what we have successfully shown, is that if there is a chord that subtends an angle of 90 degrees at the circumference, then that chord can only be a diameter. It has to be a chord that is passing through the center of the circle. All right, so, right, back to simpler things. So indeed, if we can just show that this angle is 90 degrees, then we have shown that this is a diameter of the circle that we've constructed. Okay, so let's see if we can prove that it is indeed 90 degrees. Where to begin? Oh, okay, easy enough. So we do have a diameter already. We have TR in the larger circle, and that is subtending this angle at the circumference. Okay, then we can use the fact that this angle P3 is the opposite exterior angle to this one, to angle K, and so it will be equal to 90 degrees, and therefore SR is a diameter. So let's write all of that out. Okay, so we will say angle K is equal to 90 degrees because angle in semicircle. Okay, and therefore angle P3, so nice of them to label that for us, because opposite exterior angle of a cyclic quad. Okay, in this case we're talking about cyclic quad PRKT, right? And so therefore SR is a diameter. Okay, and that's because of the converse of angle in semicircle. Cool potatoes. Wow, that was so adventurous. I'm glad I've gotten through that part of the question. Now we can move on to other things. Okay, so let's just start by highlighting all the things we highlighted before. So that's a diameter. Okay, we highlighted the cyclic quad. And then we highlighted PK and KT who are equal in length. We have also found out from our previous question that PR is a 90 degree, and so is K. Right, okay. Then we are asked to show that angle S is, whoa, how do I do that? Oopsie. Yeah. Okay, right. Oh, there we go. Right, we're asked to show that angle S is equal to angle P2. So this guy is equal to that guy. So how could we go about that? I'm just going to draw in this little circle just in case it's useful. I don't think it is, but anyway. So I mean, I am tempted to say, you know, let's call this X, right? So then this angle here will just be 90 minus X, right, in order for them to all add up to 180. And then this is an exterior angle to the cyclic quad, so it will be equal to this guy, 90 minus X. And then we would know that this is also 90 minus X because isosceles triangle. Okay. And then we know that this angle, this whole angle is also a 90 because opposite interior angles or angles on a straight line will add up to 180. So this must be x as well. Ooh, that feels like such a long dry. Vaya lang dry. But that's kind of where my thinking is at. Yeah, okay, I think I'm happy with that. So this is the first step. This is the second step. Then from there we come here. And then from there we come here. Okay, and then finally we arrive here. Okay, so let's write that out. So let S be x. So then R1 will be equal to 180 degrees minus x and 90, right? And that's because angle sum of triangle PRS. Yay! Oh my goodness. Okay, that does not look good. Let's try that again. Triangle PRS. Okay, right. So that is 180 minus x minus 90, which is 90 degrees minus x. Okay, cool. So we've got R1, and then we say T is equal to R1 is equal to, maybe let me put that on a new line, is equal to 90 minus x because exterior angle of cyclic chord PRKT. Okay, so T is 90 minus x, but T is part of this isosceles triangle. So that allows us to say angle P1 is equal to angle T, again, because of base angles of isos triangle PKT. So it will be equal to 90 degrees minus x. And then from there, we can say angles on a straight line. Maybe that's the most straightforward. So we will know that angle P2 is equal to 180 degrees minus 90 degrees, so that guy over there, and this guy, 90 minus x, and that is because of angles on a straight line, and the straight line is TPS. So that is 180 degrees minus 180 degrees plus x, which gives us x, which is equal to what we started with, right, which is equal to S. I am so sure there was probably a simpler way to do that, but so I'm definitely curious to hear if you have a different approach. Okay, so forward we go to the next one. I'm gonna start again by highlighting information we were given. So we were told that diameter cyclic chord equal chords. Okay, and we have also found out that angle S is equal to angle P2. We also know that this is a 90-degree angle, and so is this guy. Okay, right, so now we are asked to show that triangle SPK and angle PRK are similar. Okay, so because we don't have any information about the lengths of their sides, that kind of hints to me that, okay, we are going to work with angles. If we can show that they have, they're equiangular, so they have the same set of angles, then we've shown that they are similar. So I'm just also going to start by drawing out these triangles here so that I am not losing direction, okay, especially because the one triangle is embedded in the other. So SPK looks like that, and then PRK looks something like that. Okay, terrible redrawings, but anyway. Okay, and we've already been led, to figure out that S, so S is this angle, is equal to P2. So we just have two more angles to go. And we can see that, okay, SPK is equal to 90 plus whatever that angle is. Okay, do we know anything about R? I don't think we know something yet, or maybe we did find something out previously, I don't know. Okay, so I mean, I can see that, yeah, from our previous, or actually without even doing angle sum, if you look at angle triangle PRS, okay, and you look at this angle, right, it's an exterior angle of triangle PRS, so it is equal to 90 plus whatever that angle is. So that angle over there essentially is 90 plus whatever that is. And then the third angle they're equal by default. If these two match, then the other one must be the same because of angle sum of the triangles. Okay, cool. So a lot of the work we already covered in the last question, which is cool. So let me just write this down formally. But did I want to do that? Yeah, it's fine. Okay, so we already know that, so in triangles SPK and PRK, okay, we know that angle S is equal to angle P2, which we've already shown. Okay, then we also know that angle R, so let's say angle, we are saying that angle SPK, that guy, is equal to 90 degrees plus angle P2. Okay, the 90 we already showed in the beginning, so we're just going to say shown, and angle PRK, so this guy over here, is equal to 90 degrees plus S, and that's because it is an exterior angle to triangle SPR. Okay, and since we've shown that S is the same as P2, that means angle SPK is equal to angle PRK. And then finally, we can say that the remaining angle in each triangle must be equal then. So here is that. So an angle SPK, we've spoken about this angle, we've spoken about that. In triangle SPK, we've spoken about those two angles, so the remaining one is K2. So angle K2 is equal to the remaining angle in triangle PRK. So in PRK, we've spoken about P2. We've given a value for R. So the remaining one is K2. Oh yeah, it's common. Oh, silly. Okay, so K2 appears in both triangles. Funny. You know, sometimes these geometric things just get inside my brain cells. Okay, right. So K2 is common. So we don't even have to go through the pain of showing why these two are equal. We could have used that as our last angle, right? If you can just show that angle 1 in triangle A is equal to angle 1 in triangle B, and angle 2 in triangle A is equal to angle 2 in triangle B, then the last angle 3 and angle 3 of the both triangles must be equal because of angle sum in a triangle. But anyway, always good to make things harder for ourselves sometimes. Okay, and so therefore we conclude that triangle SPK is similar to triangle PRK. Okay, and the reason there is angle. Awesome. Okay, so now we go to the last part of the question. Wow, this has been so intense. Okay, so let's start by highlighting. Aren't you so glad you don't have to keep highlighting information in your actual exam? Okay, so that is a cyclic quad, and then said that these two are equal. Okay, and we have shown some right angles. Don't know if those are useful to us still, but and we also know that triangle SPK is similar to triangle PRK. Okay, so now we are further told that SR is equal to RK. Okay, then we're asked to prove that ST is equal to √6 times RK. Wow, okay, that is so interesting. So I just want to see how this knowledge affects our the proportions, the statement of the proportions of the sides based on this similarity that we proved. So we know from here that SP over PR is equal to PK over RK is equal to SK over PK, right? And we know that we've been told now that SR, where is SR? There is no SR. Okay, because yeah, we're not really dealing with. So SR. Okay, what we would be interested in is SK, which is that guy. Okay. So essentially what we've been told is, you know, if this is x, then this is also x. So SK would be 2x, right? And SR is nowhere to be seen because it doesn't have anything. Well, yeah, we're not dealing with this triangle in the similarity. We're dealing with this triangle and the larger triangle. So SR is really a little bit immaterial. Okay, but RK is x, what we've called x. Okay, and then we've got PK showing up over here, so that's cool. Who is PK? PK is this guy. So if we can find an expression for PK, we find an expression for TK, and then we have an expression for SK. So then we can work in this right angle triangle to get an expression for ST. Okay, I see. Right, so let's just write that a bit formally. Okay, so what I'm going to say is let SR be x. Okay, then we've been told that RK will also be equal to x, right? We've just been given that information. And so therefore SK will be x plus x, which is 2x. Okay, and so therefore we know that so not really a therefore moment just yet. We know that PK over RK is equal to SK over PK, because we've just shown that triangle SPK and triangle PRK are similar. Alright, and so we have PK is equal to, if we replace our PK over RK, which is x, is equal to SK, or SK rather, which is 2x over PK. Okay, and if we do our quick cross-multiplying trick, okay, which is safe to use if you know why it works. If you don't know why it works, ask and I'll tell you. Okay, so we've got PK squared is equal to 2x squared. So therefore, PK is the square root of 2x squared. And remember, always important to consider, do I need to consider the negative square root as well? In this case, it doesn't make sense to, because we know that x is a positive number because it's the length of a side, and therefore the overall square root also has to be a positive number. Okay, the x bit was not really important, but anyway, the square root we're only considering the positive because PK can't be a negative number because PK is the length of a side. Okay, so that would be x times the square root of 2. Okay, so we now have an expression for PK, right, which gives us an expression for TK because we were told that those are equal. So I'm going to come here and say TK is equal to PK, so it must also be x times root 2, and we were given that information. Okay, so now we can set up a Pythag, okay, for this triangle to figure out an expression for ST, because that's what we've been asked to figure out. Okay, so oops. So our Pythag will say SK squared plus TK squared is equal to ST squared, because Pythag said so. Okay, and we did already show that this is a 90 degree, and therefore Pythag applies. We showed that in an earlier question. But if you hadn't yet shown that it's a 90 degree, you would first have to state that it's a 90 and this is why before you applied Pythag. Okay, so SK we said is 2x squared plus TK squared is equal to ST squared. So this is 4x squared plus 2x squared. So that is 6x squared is equal to st squared. And so st will be the positive square root of 6x squared. Okay, and again, only the positive square root because st is the length of a side. It can't be negative. So that will be root 6 times x. Okay, and we know that rk is x, right? Because, yeah, we already showed that rk and sr are the same length. We were told that, in fact. So then that means st is the same as root 6 times rk, which is what we were asked to show. Okay, I don't know if there's anything I need to check on the memo, because all of these questions were proofs and we managed to arrive where we needed to arrive. So all is well. Yep, that's it for now for May 2023 paper 2 from the department. Check you for another paper another time.